Class, in our last toolbox, we discussed coordinate systems, which are mathematical systems that can be used to describe locations in space. And we also discussed how we can write functions that allow us to transform our data from one coordinate system to another. Today we're going to focus on the spherical coordinate system, which we use all the time, whether we think about it or not. The spherical coordinate system is a coordinate system that encodes locations in three-dimensional space using two angles and a radius. It's basically like polar coordinates, but with an extra angle, shown as theta in the diagram here, that determines how far off the xy plane a specific location is. The angle theta is often referred to as the polar angle, while the angle phi is referred to as the azimuthal angle. It should be pretty clear that these two angles, combined with the radius, can be used to define any location in three-dimensional space. So in the same way that we can give x, y, z coordinates to define a location or a vector, we can give r, theta, phi coordinates to define the same location. The animation on this slide shows how you can define any particular place on this sphere by changing the two angles. If you wanted to define a location either farther from the origin or closer to the origin, you would simply increase or decrease the radius. If you look at the diagram on the right, you should also be able to notice something about the range over which the two angles need to span. Typically we state that phi, the azimuthal angle, goes from 0 degrees to 360 degrees, or from 0 pi to 2 pi. This means that it sweeps all the way around the circle, as you see in the animation on the left. However, theta, the polar angle, actually goes from 0 to 180 degrees, because it only has to go from pointing straight up to pointing straight down. It doesn't have to swing back around, because we've already specified locations on the back side of the sphere using the azimuthal angle. The spherical coordinate system is actually incredibly important in Earth science. Whether you think about it or not, you use spherical coordinates all the time when you discuss locations on our planet. Our normal latitude-longitude way of describing our planet is an example of spherical coordinates. Longitude is really the azimuthal angle phi, defined with respect to the angle off of the prime meridian. Latitude is actually 90 degrees minus the angle theta shown in the diagram on the right, because we define our angle with respect to the equator rather than with respect to the North Pole. If you plug in some values for theta, you'll see that this makes sense. If theta equals 0 degrees, then latitude equals 90 degrees minus 0, which of course is 90 degrees, and we're at the North Pole. If theta equals 90 degrees, then latitude equals 90 degrees minus 90 degrees, and we're at the equator with a latitude of 0 degrees. And finally, if theta equals 180 degrees, we're at a latitude of 90 minus 180, which equals negative 90, and a latitude of negative 90 is the South Pole. In the spherical coordinate system used in geography, we assume that the radius r is equal to the radius of the Earth, which is approximately 6,371 kilometers. If you've taken many geology or geography courses, you may know that the radius of the Earth is not actually a constant value because the Earth is not perfectly spherical. The Earth is actually an oblate spheroid with an equatorial radius of 6,378 kilometers and a polar radius of only 6,356 kilometers. We seldom actually worry about this difference, however, and instead simply use that value of 6,371 kilometers for the average radius of our planet. If you ever want to be really precise, however, you need to keep in mind that change in the radius, as well as changes in radius associated with changing altitude or depth in the ocean. Okay, so we see that we are used to dealing with spherical coordinates even if we never think about it. But how do we relate spherical coordinates to other coordinate systems? Well, first let's talk about relating spherical coordinates to Cartesian coordinates in 3 dimensions. I'm not going to go through all of the equations for you, but it should be pretty easy for you to verify the equations on this slide. X equals r sine theta times cosine of phi. Let's plug in a couple equations quickly to make sure that works. First, let's try phi equals 90 degrees. If phi equals 90 degrees, we know that we're all the way over to the y-axis, so our x-coordinate is 0. Well, what happens if we plug in 90 degrees or pi over 2 for phi? Well, we have a cosine of pi over 2 in our equation, and cosine of pi over 2 equals 0. So if phi equals 90 degrees, then x equals 0. Next, let's try phi equals 0. If phi equals 0, then we have cosine of phi, which equals 1. So in that case, we know that x now depends on r and theta. Let's plug in a value of 90 degrees for theta. If we plug in phi equals 0 and theta equals 90 degrees or pi over 2, we see that sine of pi over 2 equals 1 and x equals r. This makes sense. If phi equals 0 and theta equals 90 degrees, we are pointed straight at our x-axis, so our x-coordinate is simply equal to the radius. Let's try one more set of angles. We'll ask what we get if theta equals 0. If theta equals 0, we're pointed straight up, and we know that we should have x equals 0 and y equals 0. So what do we get when we plug that into our equations? Well, for x, we have sine of theta. Sine of 0 equals 0, so no matter what r or phi we choose, if theta equals 0, x equals 0. Looking now at the y equation, it also has sine of theta, and again sine of 0 equals 0, so we have y equals 0 if theta equals 0, no matter what r or phi are. Everything makes sense so far. Last, let's look at the z equation. The z equation does not depend on phi, and that actually makes sense. Phi just rotates us around the z-axis. It doesn't determine up or down at all. So let's first try plugging in theta equals 0. If theta equals 0, we have cosine of 0, which equals 1 times r. So if theta equals 0, which means we're pointing straight up, then our z-coordinate equals r. That makes sense. Finally, if theta equals 90 degrees or pi over 2, the cosine of pi over 2 equals 0. So when we're at 90 degrees and pointing straight towards the equator, we have that z equals 0. That all makes sense. Okay, so we've checked these equations, and they allow us to transform from spherical coordinates to Cartesian coordinates. But we don't actually talk about our locations on Earth in terms of theta and phi. We talk about them in terms of latitude and longitude. So let's go ahead and plug in our equations for theta and phi as a function of latitude and longitude. We determined previously that phi is simply the longitude, so it is really simple to just plug in longitude for phi. We also determined that theta equals 90 degrees minus the latitude, so we can plug that in as well. And finally, we use the radius of the Earth, estimated as 6,371 kilometers, for r. Alright, this now lets us take any pair of latitudes and longitudes on our planet and plot them in three-dimensional Cartesian coordinates. And that's really useful, because this coordinate transformation has now transformed those kind of strange spherical coordinates into a coordinate system that's based on kilometers with the different coordinates at right angles to each other. Now that we're in a Cartesian coordinate system with units of kilometers, we can do things like compute how far apart 2 points are. Let's start with asking the question of how far apart Tallahassee and Wakulla Springs are. Well, the coordinates for Tallahassee are 30.4383 degrees north and 84.2807 degrees west. And the coordinates for Wakulla Springs are 30.2335 degrees north and 84.3052 degrees west. Alright, let's plug each of these into our equations. X equals 6,371 kilometers times sine of 90 degrees minus 30.4383 degrees north times cosine of negative 84.2807 degrees, which equals 547.4 kilometers. For y, we have y equals 6371 times sine of 90 degrees minus 30.433 degrees north times sine of negative 84.2807 degrees, which equals negative 5465.6. Note that in both of those equations, I put the longitude in as negatives since these are in degrees west of the prime meridian. Finally, we compute that z equals 6,371 times cosine of 90 degrees minus 30.4383 degrees north, which equals 3,227.6. So that is our XYZ coordinates for Tallahassee. We can then go through the same process to compute the XYZ coordinates for Wakulla Springs. Now, we remember from our toolbox on vectors that we can find the difference between two vectors by subtracting one vector from another. We find that the vector describing the distance between the two locations is equal to 1.2, 11.7, 19.6. And to calculate the absolute magnitude of a vector, or in other words, the actual distance between 2 points, we take the square root of the dot product of that vector times itself. The square root of the dot product of this vector times itself is equal to 22.9 kilometers. So that tells us that Tallahassee and Wakulla Springs are 22.9 kilometers apart. To check this, I went onto the NOAA website and I plugged in those two latitudes and longitudes to calculate the distance between them, and it told me 23 kilometers. That's pretty close. Could just be a rounding error. But let's try one more example. Let's calculate the distance between Tallahassee and Hong Kong, China. Alright, the coordinates of Hong Kong are 22.3193 degrees north and 114.1694 degrees east. If we plug that into our XYZ equations, we get negative 2413.1, 5377.0, 2419.5. If we calculate the vector between Tallahassee and Hong Kong, we get 2960, negative 10.843, and 808. When we compute the square root of the dot product of this vector times itself, we get 11,269 kilometers. Okay, that's our distance between Tallahassee and Hong Kong. Let's check it. If I plug those coordinates into the NOAA website, I get 13,817. Wait a minute, that's really different. That's more than a rounding error. So what's going on here? Well, our calculations are not wrong, and NOAA's website isn't wrong. They are just calculating different things. We are calculating the distance between those two cities in three-dimensional space. In other words, we're computing the distance of a line that cuts through the inside of the Earth. We're basically computing the length of the tunnel that we'd have to dig to create the shortest line between Tallahassee and Hong Kong. The NOAA website, on the other hand, is calculating what's known as the Great Circle distance, or in other words, the distance that you'd have to travel if you stay on the surface of the planet instead of cutting through the middle of the planet. This difference between thinking of locations in three-dimensional space as opposed to positions on the surface of our planet that we can walk around adds substantial complexities to the ways in which we visualize and compute distances on our planet. None of us are flat earthers. We all understand that we are living on a three-dimensional globe. Nevertheless, we generally experience our planet as a two-dimensional surface. When I tell you how I got to campus this morning, I say that I traveled roughly 5 kilometers west and 1 kilometer south. I don't say that I traveled approximately 4 kilometers in the x direction, 1 kilometer in the y direction, and another 1 kilometer in the z direction relative to the plane of our solar system. We think about ourselves as only traveling in the north-south or in the east-west direction. And that makes a lot of sense because we are stuck on this globe. We don't travel through the middle of it, and unless we're in a plane or on a mountain, we don't travel up in altitude either. For all intents and purposes, we can think of ourselves as living on a two-dimensional surface. But it is a complex two-dimensional surface, the surface of a globe, not a flat plane. At small spatial scales, like for instance if we're traveling across Tallahassee, we can think of ourselves as living in a simple XY Cartesian coordinate system. However, at larger scales, that's not a possibility. We know that if we keep traveling east, we will make it all the way around our planet and come back to our original location. That doesn't happen in a Cartesian coordinate system. Also, if we continue following a compass north, we'll make it all the way to the North Pole and stop there because there's nothing further north. However, if we had first walked 1,000 miles east and then followed the compass north, we'd wind up at the exact same spot at the North Pole. That also doesn't happen in a Cartesian coordinate system. As a way of visualizing our planet in two dimensions in a way that we can print on a map, we've developed many different global projections, many of which you may have heard of. For instance, this map is drawn using an equirectangular projection. The equirectangular projection basically just swaps in longitude for x and latitude for y. It's easy to map, but it does some weird things. For instance, if you look up near Greenland and the top of North America, all of the shapes are distorted. That's because really the lines of longitude should be converging on the North Pole, but they've been stretched sideways by the equirectangular projection, giving us weirdly shaped continents. Another potential projection is the Mercator projection. The Mercator projection was designed to fix this issue. It is similar to the equirectangular projection, but it stretches things out in the vertical direction, with greater spacing between lines of latitude the further we get from the equator. By computing the projection in this manner, we preserve the shape of different continents. However, the Mercator projection also does some weird things. It stretches polar regions and makes them look much larger than they should be. For instance, compare the sizes of Greenland and Australia. On a Mercator projection, Greenland looks like it is much larger than Australia, when in reality Australia is more than 3 times larger than Greenland. This is an issue with the Mercator projection. When I was in grade school, I couldn't understand why Australia was a continent and Greenland was only an island, when Greenland looked so much larger in the Mercator projection maps that were hanging on the walls of our classroom. Another projection, the Malwide projection, fixes some of these issues. It is an equal area pseudocylindrical projection that preserves the relative area of different regions of the map. However, it introduces some other issues. For instance, it does not perfectly preserve the shape, and it also introduces substantial issues with calculating angles. Another special type of projection is the stereographic projection. The stereographic projection is conformal, meaning that it preserves angles, and it's really useful for producing maps of the South or North Pole. However, it does really strange things if you try to use it for larger regions of the globe. Okay, all of these are different ways of visualizing the three-dimensional globe in 2 dimensions. So let's talk about the mathematics behind this. First, let's spend some time talking about transformations from 3 dimensions into 2 dimensions. In the last toolbox, we focused on transformations from 2-dimensional coordinate systems to other 2-dimensional coordinate systems. Earlier in this toolbox, we talked about transforming spherical coordinates to XYZ Cartesian coordinates, which was an example of a 3D to 3D transformation. Those obviously make sense because in both cases we are simply talking about transformations that were just different ways of specifying the exact same point. When we take a transformation from 3-dimensional coordinates to 2-dimensional coordinates, we're doing something that is a bit different because we're really throwing out data. What does that actually mean? Well, let's imagine that we've got 3-dimensional XYZ coordinates of all the buildings in this city here. Well, one way that we could map this data into 2 dimensions is to use the following very simple 3D to 2D transformation. We'll just say that our new 2dx is equal to our old 3dx, and our new 2dy is equal to our old 3dy. And the old z or height variable doesn't matter. We're basically just throwing away the z or vertical data. If you think about it, this mapping system is basically just what we would get if we plotted the shadows of all of those structures when the sun was directly overhead. And it would give us images that look like this. We just have the shadow of all of those buildings cast on the ground. We no longer know the heights of those buildings, but we do know their lengths, widths, and locations. That's not the only 3D to 2D transformation that we could use, however. We could also imagine a 3D to 2D transformation that would map the shadows of that these buildings would cast if the sun was at a 45-degree angle. If the sun was angled perfectly along the xy direction, we might use the transformation new x equals old x plus z and new y equals old y. This basically stretches some of our buildings out horizontally, with the tallest buildings getting stretched the most. All those other projection systems we talked about are essentially doing the same thing, just in more complicated ways. They are taking locations on this rotating orb that we live on and mapping them in some way or other onto some form of a 2-dimensional grid that helps us visualize, navigate through, and/or calculate distances around our planet. Alright, let's talk about computing some projections from spherical coordinates into some coordinate systems that might actually be useful to us in environmental sciences. Let's imagine that some city planners came to you and asked you to help them plan an environmentally friendly city. So you carefully laid out a grid with blocks that were all 200 meters by 200 meters. Every fifth road you decided to make wider and designate only for mass transit zero-emission buses and electric vehicles. You also put in subway lines every 5 kilometers, which are shown in blue on your map. You made sure to mix residential and commercial zoning to encourage walkable districts, and you also zoned most of the city for apartment buildings that ensure that it takes up less space for each person. You created an ordinance mandating that all construction includes rooftop solar. Then you put several large parks in your city, shown in green on the map, and connected them all by wildlife corridors that ensure genetic exchange between different populations of animals and plants living in your city. But now you actually need to tell construction companies where to start putting in the roads, and they need actual latitude, longitude coordinates, not just the XY coordinates that you use to grid your city. So in other words, you've currently got a city map laid out in XY coordinates where your XY coordinate refers to kilometers east of the city center and your Y coordinate refers to kilometers north of the city center. And now you need to translate this map into spherical coordinates of latitude and longitude. In other words, it's time for some math. Alright, let's think about what spherical coordinates actually mean if we're walking on the surface of the planet. Let's imagine that we're standing at the equator and we've walked along 1 degree of longitude. What we've done is walked part of a circle along the surface of our planet, carving out a 1 degree angle along that circle. So we can actually calculate the distance that we've traveled. The circumference of a circle is 2 pi times the radius r, and we've traveled 1 degree or 1/360th of the circumference, so we can write that our distance equals 1 degree divided by 360 degrees times 2 pi times the radius of the Earth. And we know the radius of the Earth is approximately 6,371 kilometers, so we can plug that in and calculate that at the equator, if we travel 1 degree of longitude, we've traveled approximately 111 kilometers. Next, let's consider what would have happened if we had started out at the equator again, but this time we traveled north by 1 degree of latitude. In this case, we've again swept out a curve over the surface of our planet. The circumference of the circle that we're traveling along is again going to be 2 pi times the radius of the Earth, and again we've traveled 1/360th of the way along that circle, so we've traveled 111 kilometers. This seems pretty easy so far, and the distance between degrees of latitude is always pretty much 111 kilometers. However, the story is more complex with longitude. Last time we started off at the equator. Let's think about what happens when we start somewhere other than the equator. Let's imagine that 2 people start off at different spots on the planet. One of them starts off at the equator, the other starts off at a latitude of 60 degrees north. Both of them travel east for a distance of 90 degrees or 1/4 of the way around the planet. The person who started off on the equator followed the red dashed line's path. The person who started off 60 degrees north traveled on the orange dashed line. Looking at these 2 lines, it's pretty clear that the person who started on the equator traveled much further than the person who started off at 60 degrees north. This is because, while they both traveled 1/4 of a circle, the radius of the circle that the person on the equator was traveling around was larger than the radius of the circle that the person at 60 degrees was traveling around. Let's get rid of our city diagram for a moment to try to understand this. The diagram on the right shows a cross-section through the Earth. The red dashed line shows a cross-section going from the center of the Earth to the equator, so it represents the radius of the path traveled by the person who started at the equator. The solid orange line is the line drawn from the equator to a point on the surface of the planet at 60 degrees north latitude. By definition, therefore, the angle between this line and the red line has to be 60 degrees. Hopefully this sort of a diagrammatic setup looks familiar to you because it is basically just the unit circle. And if we draw a line from the end of the orange line to the line that connects the poles, this new dashed line should be equal to the radius of the circle that someone traveling along the 60 degrees north would be following. This new dashed line is also clearly the opposite side of a triangle with an angle of 30 degrees and a hypotenuse equal to the radius of the Earth. The dashed line is thus equal to 6371 times the sine of 30 degrees, which is equal to 3185.5 kilometers. Alright, and since that is the radius of the circle that someone traveling around 60 degrees north is following, we can plug that back into our other equation, and we calculate that the person following the orange dotted line traveled 5,004 kilometers. And that is compared to 10,008 kilometers traveled by the person traveling along the red dashed line at the equator. Okay, so let's generalize what we've learned a bit. If you are traveling north-south, following any line of longitude, then you will always go eventually from one pole to another pole, so you're always traveling along a circle that is equal to the radius of the Earth. So we can write that the distance traveled will be equal to the degrees latitude that you've traveled divided by 360 degrees times 2 pi times the radius of the Earth. On the other hand, if you are traveling east-west, you need to write a modified equation that takes into account the fact that the circle you are traveling on gets smaller as you get closer to the poles. This equation states that the distance you've traveled in the east-west direction is equal to the degrees of longitude that you've traversed divided by 360 degrees times 2 pi times the radius of the Earth times the sine of 90 degrees minus the latitude that you're traveling at. This means the distance between lines of longitude varies depending on which latitude you're at, which of course makes sense. We can also check to see what happens if we calculate this at the equator with a latitude of 0 degrees. Since the sine of 90 degrees is the same as the sine of pi over 2, it tells us that at the equator we're traveling along a circle equal to the radius of the Earth, which checks out and makes sense. Next, let's go back to our city grid and see how we can use these new equations to translate our city grid into latitude and longitude coordinates that we can give to the construction companies who need to start laying out our roads and planning our parks, buildings, and subways. Alright, let's think about what those equations mean for our grid, which is laid out in XY Cartesian coordinates, defined as kilometers east or west of the center of the city, and kilometers north or south of the center of the city. Let's start off by talking about the north-south dimension because that's really the easiest to deal with. Let's think about traveling 1 kilometer north from the city center. That would put us at a location of 0, 1 in our XY coordinate system. What latitude and longitude would that trip take us? Well, of course, that depends on what the latitude and longitude of the city center actually is. So let's define that. But for now, we'll keep things generalized and say that the center of our city is at a latitude of cc lat for city center latitude and a longitude of cc lon for city center longitude. Now we could simply plug in values of 30 degrees north and 84 degrees west if we wanted to set up our city near Tallahassee, but we'll keep it generalized instead, just so that we can hopefully use the equations we'll develop now for any city that we decide to build anywhere else. Alright, so now we can use that equation for traveling north-south and rewrite it as 1 kilometer equals the latitude we are trying to find minus city center latitude, because that's the distance that we've traveled, divided by 360 degrees times 2 pi times the radius of the Earth. And we can simply rearrange this equation to find that our latitude 1 kilometer north of the city center is equal to 360 degrees divided by 2 pi times the radius of the Earth plus the city center latitude. And since we know that we have only traveled north, not east or west, we know that our longitude is equal to the city center longitude. So our transformation has to take the point 0, 1 and transform it to 360 degrees divided by 2 pi times the radius of the Earth plus cc lat, comma, cc lon. Okay, let's try one more example for traveling north from the city center. This time we'll look at the point 0, 5, which would be the y-coordinate of our next subway line. This time, we have 5 kilometers equals our new latitude minus city center latitude divided by 360 times 2 pi times the radius of the Earth, which rearranges to the latitude equals 5 times 360 divided by 2 pi times the radius of the Earth plus the city center latitude. So we know that our transformation should take the xy coordinate pair 0, 5 and translate it to 5 times 360 divided by 2 pi times the radius of the Earth plus cc lat, comma, cc lon. Hopefully, you can see from this analysis that we can pretty easily write an equation relating the latitude of any point in our city to our y-coordinate. Latitude as a function of y equals y times 360 degrees divided by 2 pi times the radius of the Earth plus the city center latitude. Alright, next, let's think about traveling east or west. Let's start at the city center and travel 1 kilometer east. Now, using our east-west equation, we can write that 1 kilometer equals our new longitude minus the city center longitude divided by 360 degrees times 2 pi times the radius of the Earth times the sine of 90 degrees minus the city center latitude, which is of course the latitude that we're traveling in. We can then rearrange to ln equals 360 degrees divided by 2 pi times the radius of the Earth times sine of 90 minus cc lat plus cc ln. So this performs a transformation from 10 to cc lat, comma 360 over 2 pi times the radius of the Earth times sine of 90 minus city center lat plus city center ln. Okay, it seems like we're on our way to a general formula for longitude as well, but let's try one more thing. Let's travel 1 kilometer east from our location 1 kilometer north of the city center. It should be clear that we can basically use the same equation, except that our latitude is no longer the city latitude. Instead, it is the latitude that we previously calculated for this location 1 kilometer north of the city center. Alright, that's all well and good, and we can write that equation. But let's try traveling 1 kilometer north from our location that was 1 kilometer east of the city center. On our XY Cartesian coordinate grid, we should wind up at the exact same place, of course. But this time we know that we're starting out at our longitude of 360 degrees divided by 2 pi times the radius of the Earth times sine of 90 degrees minus cc lat plus cc ln. And since we're going straight north, our longitude is not changing, so it is still at that value. But of course the equations in teal and in orange are not actually at the same longitude, despite being at the exact same XY coordinate grid point. This is actually a general issue with trying to translate our spherical coordinates onto a simple XY plane, and introduces a strange fact about traveling on our planet. If you travel 1 kilometer north and then 1 kilometer east, you'll wind up in a slightly different place than if you travel 1 kilometer east and then 1 kilometer north. Let me illustrate this issue in a slightly more clear way. Let's say that we start off at a point on the equator. You first travel a distance of 10,000 kilometers east. This is roughly 1/4 of the circumference of the Earth, so you've made it 1/4 of the way around. Next you travel 6,667 kilometers north, which will take you up to approximately 60 degrees north. Okay, good. But now let's envision another journey starting at the same point and first going 6,667 kilometers north, so approximately to 60 degrees north, and then traveling 10,000 kilometers east. This time we're traveling the same linear distance, but we're traveling along a circle with a much smaller circumference, so we're actually making it halfway around the planet. Both trips took us 10,000 kilometers east and 6,667 kilometers north, but they ended in different places because we took those trips in different orders. This is why there's so many different projection systems, and this is also why we came up with 2 different answers for how to translate from our XY to our lat-lon coordinates. Hopefully you can see that those equations give us 2 different options for defining our transformation from XY to lat-lon coordinates. Transformation 1 is derived from the orange equation along with the equation that we already wrote for latitude. This transformation tells us that the longitude will only be a function of our x-coordinate. This is equivalent to going east first and then north. The equation guarantees that all of your streets run perfectly north-south or east-west, and it sets your block length to be the 200 meters that we wanted originally at the city center. But as we get farther and farther from the city center, the length of blocks will shift to slightly longer if we're moving towards the equator, or slightly shorter if we're moving away from the equator. Transformation 2 is derived from the teal equation, and it basically substitutes your actual latitude from the latitude equation in for the city center latitude that was used in the equation in transformation 1. Substituting this in now makes your longitude a function of x and y because you are making that slight correction that now you will travel a slightly shorter or slightly longer way around the planet when you go 1 kilometer, depending on what latitude you're at. The second transformation will thus ensure that all of your blocks actually are perfect squares of 200 meters by 200 meters. However, since the longitude of a particular north-south running road is no longer constant, but varies slightly with y, you know that your north-south streets are no longer running perfectly north-south. They are slightly off. We thus have a choice to make. We can either choose a transformation that preserves the direction, with streets that run north and south, or we can choose a transformation that preserves the shape, giving us perfectly square blocks. So if you want to create our nice, well-planned, eco-friendly city, we're going to have to decide whether to have perfectly north-south running roads or perfectly square blocks. The reality is that, over the span of a city, these differences are really not that significant, and people really wouldn't notice that much. But over the scale of some of our larger national parks, and especially over the scale of countries, continents, and ocean basins, these choices can be quite significant. And really, what we're talking about is just different projection systems, like those projections we discussed earlier in the toolbox. And we simply need to decide which projection or transformation is most appropriate for our purpose. The one other caveat that I want to mention is that these equations don't work if either the north or south pole is included in your city. If you're ever asked to plan a city down in Antarctica that includes the South Pole, come and talk to me, and we'll go through the more complicated math that you'll need to use. For now, go ahead and do the online quiz before class.